In this video, we will establish the adiabatic invariance of the action variable in classical dynamics. Before we start, we're going to set the scene by discussing Maupertuis's principle, which states that the variation of the integral of p dq minus h dt equals 0 is equivalent to Hamilton's equations for a Hamiltonian h depends on q, p, and t. So to show this, delta the integral of p dot q minus h dt will have it going from time t0 to t1 in both cases. So performing the variation, delta p q dot plus p delta q dot minus dh by dq delta q minus dh by dp delta p dt. That variation is 0. So we're going to write that as the integral t0 to t1 delta p into q dot minus dh by dp plus this term here I'm going to write as p delta q all dot plus minus p minus dh by dq, and that's all multiplied by delta q dt is 0. So this term integrates out to give me that's t0 t1 plus the integral t0 to t1 delta p q dot minus dh by dp minus delta q p plus dh by dq dt is 0, where we impose the boundary conditions that delta q equals 0 at t equals t0 and t equals t1. We're also going to impose delta p equals 0 at these points. It won't be necessary for this part of the calculation, but is useful more generally. Since delta p and delta q are arbitrary in phase space other than this boundary condition, this implies q dot is dh by dp and p dot is minus dh by dq. These are Hamilton's equations. We might notice that total dh by dt is partial dh by dt at constant q and p plus partial dh by dq times q dot, which from here is dh by dp plus dh by dq times q dot, oh sorry, I've already done that one, dh by dp, p dot, and that's partial dh by dt at constant q and p. This is a result we will make use of later on. Now suppose we have p dq minus h dt is capital P d capital Q minus capital K dt plus df. We can notice that if we take the exterior derivative, we end up with this quantity here, and here we end up dp d capital Q minus dk dt, and we're using the fact that d squared equals 0, so the last term does not make any contribution. Just put a wedge there. This is the symplectic form on the extended phase space in variables q, p with Hamiltonian h, and this is the similar thing in the variables capital Q, capital P, Hamiltonian k. So this shows that the symplectic form is preserved under this transformation. So this is symplectic and therefore canonical. Okay, let's rearrange this equation, and I'll rewrite f as f1 as is conventional. So df1 is p dq minus capital P dq minus, let's say, plus k minus h dt. From this you see that f1 should be regarded as a function of little q, big Q and t, since these are the differential terms in the expansion. And then you get the partial derivatives df1 by d little q at constant capital Q and t is little p, df1 by d capital Q, little q and t is minus p, df1 by dt capital Q and big Q, little q and big Q is k minus h. However, f1 is not the most useful thing you can use. You can have f2 as f1 plus qp. The differential relationship is then little p dq plus q dp plus k minus h dt, from which you can see that f2 should be regarded as a function of little q, big P and t. We have that df2 by d little q, capital P and t is little p, df2 by d big P, little q and t is big Q, df2 by dt a little q big P is k minus h. As an example, if f2 were little q big P, this partial derivative gives little q, gives big P, and that's equal to little p. This one tells me that little q is big Q, and this tells me 0 is k minus h, and this is the identity transformation. And because the identity is a type 2 generating transformation, it's one of the reasons why it turns out to be the most important of the lot. There are two others. f3 is f1 minus qp, and that will turn out to be a function of big Q, little p and time. And f4 is f1 minus little q, little p plus big Q, big P. And that is a function of the momenta. And it's easy enough to work out the relations here. Now let us try and apply the type 2 function to generate the action angle variables. Under this transformation, it's conventional to write S to be F2. We'll write theta for the angle variable, the Q, and P becomes I. So just to recall, ds by d little q at constant I and t will be little p. ds by di q and t is theta ds by dt at constant q and I is k minus h. The idea for action angle variables is to arrange it so that the new Hamiltonian, the old Hamiltonian, which is q of h of q and p, can be written as a function solely in terms of the new momenta. We can take this equation and integrate it up. So you have the integral of p dq. If we want I to be constant, well, I equals constant from here. I can always rearrange this. Show that I equals constant is equivalent to h is constant. So let's say that h equals e. And we'd also set time to be constant, but nothing here is going to depend on time, since I haven't made my Hamiltonian have any time dependence. We can take I to be anything we like at this stage, and it turns out to be useful to define I to be this contour integral over h equals e. From this, we can write down Hamilton's equations. Now k is going to be the same thing as h, because there's no explicit time dependence in here. We have I dot is minus dk by d theta, which is 0, because h and k are the same thing and there's no explicit dependence on theta. So I is constant, but that's not a surprise because a Hamiltonian which does not depend on time has a total time derivative which is going to be 0. We proved that earlier on. Now theta dot is dk by di, which is the same thing as dh by di, and that's just some function of I, we call it omega, of I. Now theta, if you recall, here is ds by di, a constant q and t. So if we integrate over a full period, the change in theta is d by di of delta s. But the change in delta s over a full period is just 2 pi I. So that's 2 pi. Therefore, theta varies at a constant rate and changes by 2 pi over a full period. So the periodic time is 2 pi over omega, is 2 pi di by de, if we write the value of the Hamiltonian to be the energy. Next, let's discuss adiabatic invariance. So now we consider H, Hamiltonian, which has some time dependence, but the time dependence only comes in through a function lambda, which is in some sense slowly varying. We'll have lambda dot equals order epsilon, lambda double dot is order epsilon squared. So epsilon here is a small parameter. We say the quantity I is an adiabatic invariant if I of t minus I of 0 is order epsilon for all timescales t in, say, 0 to t0 over epsilon. It varies like 1 over epsilon. So we have a diagram. Suppose that's our starting point. Then we want it to change to be no more than order epsilon when that's t0 over epsilon. An example: if j was some function which was order epsilon squared, then j of t minus j of 0 would be the integral 0 to t of j of t dot dt, which would be order epsilon squared t, and if epsilon t is order 1, that's order epsilon, which is what we want. However, most adiabatic invariants do not obey this. If I were j plus order epsilon, and j dot is order epsilon squared, then you can see that I at time t minus I at time 0 would be order epsilon from there, plus order epsilon, which of course is just order epsilon. Then I is an adiabatic invariant. So the idea is that if this was j, I is just tied to j, and its change over long periods of time is small, although its rate of change, I dot, need not be small in any sense. Let's see how we can use this to prove the adiabatic invariance. So we start off with h of q, p, and lambda of t as before. We write s to be the integral of p dq over h equals e. We're just constructing the action angle variables in this case, we'll write I as 1 over 2 pi integral of p dq over h equals e. We know that k is equal to h plus partial ds by dt at constant I and q. Now all time dependence comes in via the function lambda. So this depends on lambda, and therefore we have h plus order lambda dot. The key to the proof I'm presenting is to construct j time to be 1 over 2 pi, the integral of I d theta over the contour k equals constant. This is just constructing the action variable from the action angle variables that we have already constructed. So it's an exact analogy to this, and that will be from theta equals 0 to 2 pi. What one should think about it in that sense. Now, this condition here means that I can replace the contour integral, let's write it exactly, I d theta, by integrating over h equals a constant plus order lambda dot terms. But if you recall, I was a function of h and time. This is time equals constant as well. So this is just I at time t plus order lambda dot. Next, let's work out total j by dt. We notice that j is a function of k and t only, or if you prefer to invert that, you get this thing. This is because it is the action variable from the variables I and theta. So that's partial dj by dt at constant k plus partial dj by dk at constant t times total dk by dt. But total dk by dt is the same thing as partial dk by dt at constant I and theta. This holds for any Hamiltonian, as we saw earlier on in the video. But we recognise this as partial dj by dt at constant I and theta. So that's partial d by dt at constant I and theta of this thing here, I plus order lambda dot. And I can get rid of that because I is held constant. That gives me order lambda dot squared terms and order lambda double dot terms. So that's order epsilon squared. So we have j dot is order epsilon squared, and from here we have j is I plus order epsilon. So between those two, those give me the fact that I is an adiabatic invariant of the system. The nice thing about this proof is that the construction of the adiabatic invariant and its proof fits in so nicely with the theory of generating functions and the like. You don't need the time averaging, which is typical in other proofs. Effectively, the averaging comes from this expression here, and it fits in so naturally within the general framework.